Aloha, this is Roger Brewer, John Peard, the Hawaii Department of Health. This is the second of a four-part webinar series on the use of decision unit and multi-increment sampling methods to investigate contaminated soil and sediment. In the first presentation, John discussed the use of systematic planning to develop very well thought out work plans for characterizing a site. He discussed the importance of carrying out a very thorough phase 1 review of the history of the site, including visiting the site and even interviewing people who used to work at the property, who currently work at the property. You use this information to develop a well thought out conceptual site model so you understand the layout of the site and the history, and use this information then to designate areas targeted for characterization. We refer to these as decision units. So in each decision unit then a sample or samples are collected, and then the data for each decision are compared to screening levels or incorporated into a risk assessment. And then some decisions are made on the need for additional actions at the site. So in this presentation today, we're going to go over more details of decision designation in the field. We're going to go through a lot of examples of work mostly done in Hawaii, but in collaboration with other people in other areas of the U.S. The primary reference, again, for our presentations is the Hawaii's Technical Guidance Manual. We're going to focus again on Section 3 today, systematic planning, and decision units are really the most important part of this section. You see the reference below with the web link. Quick review on decision units first. So decision units I like to think of as satellite images, where the goal is to set the desired resolution of an investigation up front. So once you carry out the investigation, then you're already at a stage where you can make decisions and minimize the need for additional field work. So the best definition for a decision unit is the volume of soil or sediment, water, air, whatever, that you would send to a laboratory as a single sample if possible. It's not usually possible, so a representative sample has to be collected from that targeted area, that targeted decision unit, and then analyzed and used to represent the sample, the decision unit. John discussed two types of decision units, and this should be familiar with anyone who's done any field work. So we discussed source areas or spill areas where there's some reason to suspect contamination in a specific area of a site, shown here in these left-hand photographs. Maybe a waste oil pond, the oil is drained and you're confident the soil underneath that is contaminated. A lot of times you can see it in the field. Other times you may not be able to see anything. In the bottom left-hand corner, former transformer pads, some concern about PCB contamination around the pad. So these are spill areas or source areas. Again, very common concept. If you're concerned about risk assessment, then a very common term is exposure area. So this could be someone's backyard. In this case, this particular backyard was suspected to be contaminated with lead, and children were playing in this area and such. So we designated as a specific exposure area for characterization. And then below this, a commercial industrial facility. The entire open area of an unpaved commercial industrial facility might be considered another type of exposure area. So a key point to keep in mind here is each decision unit has a specific objective or specific question designated up front. So for example, in the exposure area, does the concentration of lead in this part of the backyard, or the entire backyard, exceed some target screening level? Or for arsenic, PCBs, whatever, does it exceed some target acceptable risk? And there's also associated with each DU then is a decision statement. So once you collect the data, then you're prepared to carry out some action on that decision. So in this case, if the concentration of lead in this backyard exceeds Hawaii's screening level of 200 ppm, then that entire DU will be excavated and removed, or maybe it'll be capped. So that's a key point. Every DU has a specific objective designated up front and a specific decision statement assigned to it afterwards. All these ideas and these approaches are intended to minimize the need to go back and reinvestigate a site or spend a lot of time after you have the data wondering what to do with the data next. Now, a key point here is within each decision unit, the objective is to determine the true or the mean concentration, if you want to use that term, for the decision unit volume of soil. You may even be looking at a specific soil particle fraction. Typically, the decision unit we're looking at includes the less than 2 millimeter fraction of soil. For direct exposure risk, you may be focusing on the less than 250 micron fraction, or even 150 micron fraction. So that's another key point to remember. So when you collect a sample, or in the past when we were attempting to characterize DUs with discrete samples, the key point is that the sample must capture and represent the smaller scale variability within a DU. Again, as if you could excavate the entire DU amount of soil, send it to a laboratory for sampling and testing as a single sample. A key point to bring up, which something I certainly missed in the first part of my career, is these screening levels that are published, including Hawaii's, US EPA's regional screening levels, and California's environmental screening levels, other state screening levels. They apply to the DU as a whole. They were never intended to apply to individual discrete points or discrete samples within a decision unit. This is a mistake that we made early on, at least I did in my career. This was one of the causes of a lot of the problems with environmental investigations, where there was no clear endpoint in sight, failed confirmation samples and such, and we'll go into that in a lot more detail tomorrow. Now, we talked about early on the use of multi-increment soil samples to characterize the decision unit. And again, tomorrow we'll look at this in more detail, the difference between discrete soil samples and multi-increment samples. So a multi-increment sample is simply a single sample of soil collected from a large number of points, usually 30 minimum to 75 or even more, within a specified DU. So at each one of these points we collect what we refer to as an increment of soil, typically 20 to 50 grams. And the soil is combined into a single sample for that decision unit. So the minimum sample mass is governed by sampling theory. Again, we'll talk about that in the third presentation. If you're looking at less than 2 millimeter fraction of soil, the minimum mass you need to collect is around 1 to 2 kilograms. And the soil sample that you collect is carefully processed and subsampled at the laboratory to retain the field representatives. If you're looking for non-volatile contaminants, then the laboratory will typically dry and sieve the sample to less than 2 millimeters or smaller fraction if needed. Then they'll go through and subsample that, collect a subsample for testing from 30 to 50 points or more within that sample for testing. So in this case, the data you get back from the laboratory represents the sample you sent to the laboratory. The sample you sent to the laboratory represents the targeted area where you collected the sample from in the decision unit. So how do you know that one sample is representative? Well, similar to the way laboratories test or do a quality control test for sample method precision, and you'll collect replicate samples from a batch of similar DUs. So example, out of every 10 DUs in one of these DUs, you'll collect triplicate samples. And again, we'll go into this tomorrow. And you compare the results between your replicate samples to get an idea of your sampling method precision. This approach is independent of the size of the DU. If it's the size of your cubicle or your table, or several thousand acres or 100-acre field, the same sampling theory rules govern. You collect a single sample from a minimum of 30 to 75 points, minimum sample mass 1 to 2 kilograms. So again, the key point is how you designate the DUs. The sampling part actually becomes pretty simple, at least in concept. Logistics, it may be a little bit more complicated. Now, I like to think of a discrete soil samples as a single increment sample. We'll talk about this again tomorrow. In the past, the idea was in the 1980s that within some targeted spill area, that any sample within that area should be relatively similar, the concentration of the contaminant. So you only need to collect one sample to represent that area. Now we know that's not the case. So let's start looking at some examples. First, we'll look at some example exposure area decision units. This is a former skeet range on the island of Oahu. They operated from the 1930s to 1970s. So in general, they were shooting toward the ocean at this skeet range. So you might imagine the ground in front of where they were shooting and along the edge of the ocean was littered with bullets, and especially skeet fragments and also lead shot. Here's what the area looks like today. So now it's a residential development. It was constructed right on top of the former skeet range. If you go out along the reef or even in the sand walking along here, you can see little bits of lead shot in the sand and in the reef areas. So we were concerned about exposure to lead. along the beach areas. So first thing we did was we designated the beach area behind each house is a backyard decision unit, the same we would in any other area, any other situation. So we had two specific investigation questions. One was, does lead in the fines fraction of a backyard decision unit exceed levels for potential chronic direct exposure risk? The second question was, is there lead shot present in the DU that could pose either short-term acute risk or breakdown in the future and contribute to longer-term risk? So again, these decision questions are stated up front as we designated the decision unit. Here's what we found in each of the decision units. We had a total of 23 backyards that we tested. So in each of these DUs we collected a single multi-increment sample. Again, we're looking at that again more tomorrow. Just to give you a quick idea what we found, the lead shot was identified in the red decision unit, so 6 or 7 DUs. So we're concerned about potential short-term risk from kids, especially children, playing along the beach in those areas. Only one of the multi-increment samples collected from soil in the backyard actually exceeded our screening level. So that was an example of use of exposure area decision units. Let's look at spill area decision units real quick. Again, this is nothing new to most people who have been doing field work. Here's a map from the 1980s, U.S. EPA guidance for investigation of contaminated soil. A quote from the Data Quality Objectives for Remedial Response Activities guidance written in 1987. So to apply this grid-based discrete sampling method, the shape and the size of a contaminated zone must be known at least approximately. And typically the location of suspect contaminated zones are also known at least approximately. So the concept again is spill areas decision. It's nothing new, but the sizes of suspect spill areas was used in the past to designate the grid size for discrete samples, and we'll discuss tomorrow in the next presentation why this didn't work as well as they thought it would. Here's an assumption made early on in the development of investigation guidance. The implicit assumption that contamination is likely to be uniformly present anywhere within the sampling area is reasonable. So 1985 verification of PCB spill cleanup. So the concept then was that because the contaminant was uniform within the spilled media, say within the electrical dielectric fluid or wastewater from an industrial plant, then it made sense at the time before they tested that it would also be uniform in the soil. So you could collect a sample of soil, any mass, any location within the spill area, and you'd expect to get a similar concentration of contaminant. So again, we'll talk in the next presentation. We'll discuss whether or not that's the reality in the field. So let's look at some examples of combined exposure area and spill area decision units. That's typically the way sites are investigated now. The way I like to start the investigation of a site is the first step is just designate the entire property as a single decision unit. That's the best way to start. And then as you understand more and more about the site, to start to break it up into smaller and smaller decision units based on suspect spill areas, exposure areas, and such. So this is a case of a 10-acre former maintenance yards being redeveloped for a shopping mall right adjacent to a former wood treatment facility. We knew ahead of time the wood treatment facility was contaminated with arsenic and dioxins. We also knew that on the right side of this property was a former railroad line that went through there. So with railroads, there's always concern about arsenic contamination. They used to spray arsenic-based weed killer along railroad tracks, really from the late 1800s through the 1900s, to kill weeds along the tracks. It was a big problem back then with trains going through your town in the middle of the night and catching the weeds on fire and burning the train, your town down. So arsenic contamination around railroad tracks is a common concern. Also a small spot within this maintenance yard, which otherwise is fairly clean as far as we knew of petroleum contamination. And you can see it in the field, so not a big surprise. So first designating decision units, let's focus on the former wood treatment area. So along the perimeter of the wood treatment area, we're concerned about arsenic and dioxins. It could have contaminated the edge of the property that's going to be redeveloped for a shopping center. So you see these long, narrow spill area, source area decision units designated right along the edge of the property. So we keep these intentionally small so we can try to isolate any contamination present. We thought initially that the contamination should be right along the edge, just within 20-30 feet of the property. In the right-hand side of this picture, we designated a little bit larger spill area or source area decision that we suspected could be contaminated with arsenic and dioxins based on the topography of the site. And the other part of the property, just a single long narrow spill area, source area decision along the property line with the former wood treatment area. If you went out to the site, this is actually uphill. We didn't really expect to find any contamination here, but we designated a source area decision there anyway. So how about the railroad tracks? Along the railroad tracks, if we were assuming this part of the property could be left unpaved, uncapped in the future, and we had a moderate suspicion that this area could be contaminated with arsenic. So we settled on a default DU size of 0.5 acres, half an acre for commercial industrial exposure. We really could have made it larger than that for a typical commercial industrial site of this type complex, but we set it at 0.5 acres just to keep the area and volume of soil fairly small. And remember, decision units have a specific volume of soil associated with them. In this case, we're looking at the top 6 inches of soil, so for half an acre DU area, it's about 1,000 cubic yards of soil. And we're going to collect a representative sample on each one of these DUs. And again, if the DU fails our screening level for arsenic, then that DU will be excavated. So you really want to work with your remediation people to see if they're comfortable with excavating 1,000 cubic yards of soil at a time. They may want something smaller if there's really strong suspicion it's contaminated. Now, along the edge of the railroad tracks, we designate what we refer to as perimeter DUs. And we're hoping that these small DUs here will come up clean, so we'll be able to isolate the contamination, or any contamination present within the former railroad track area. You see another decision unit spill area designated in the former petroleum contaminated area. It's recognized on the site. It's really small, very easy to see in the field. You see staining. These are easy decision units to designate. You don't really need perimeter decision units around it now, because we know exactly where the contaminated soil is. Well, we could collect confirmation samples once it's excavated. So those are the main DUs for this site as far as contamination goes. We still have a very large part of the site that remains untested. So one thing consultants in Hawaii started doing several years ago, and especially their clients have been asking for, is to test the entire property just to make sure you didn't miss anything. So in this case, no suspect source areas. So the consultant divided the rest of the property into very large exposure area decision units, from 1 to 2 acres in size. That's about as large as we were comfortable with for this type of redevelopment in terms of commercial industrial worker exposure. So 1 to 2 acres equals 2 to 3,000 cubic yards of soil. They're fairly confident that there's no contamination is present within this area. But imagine if one of these large DUs failed, then suddenly you're stuck with 2 or 3,000 cubic yards of soil to dispose of or to cap or something. So they're taking a bit of a chance setting decision units this large, but in this case it turned out to be warranted. No contamination was identified in these areas. So this is a great example of designating decision units up front at a resolution or a scale that you're comfortable with making decisions once you get your data back from those. You really want to avoid going in and doing a site investigation and then coming back and not being able to make a decision on a decision unit. Maybe you think it's too large suddenly. Well, you should have thought about that up front, because you want to avoid going back do additional investigation at a site. Here's another example. This is a former municipal incinerator on the island of Oahu again in Honolulu. 10 acres. It is no longer operational. They were going to develop it as a commercial or use, or especially for a potential soccer park. So in this case, the white area in the middle of the slide, the picture here is the former incinerator. Ash came out of the back of the incinerator and was put into trucks, we thought anyway at the time, in this small area here within the outlined in black. So this is the target spill area, source area behind the incinerator. Municipal ash tends to be contaminated with lead, several thousand ppm. That was the main contaminant of concern at this site. So in the suspect spill area, they divided the area into 4 fairly small decision units just to get good resolution, especially for remediation. So you see these 4 small decision units within here. Now around the edge of where the ash was coming out of the incinerator, you see these purple DUs. Again, they're fairly small. They're only covering a few thousand square feet, 100 or 200 cubic yards each. And early assumption, I guess hope, was that these perimeter decision units here would all come up clean, and very quickly they identify and isolate the main contamination, and in one go they can go in, investigate the site, and set up a remediation plan as needed. Now the rest of the property again was 10 acres. And again, because it was going to be used potentially for a park, initially not suspected to be contaminated, they divided the entire rest of the property into 10,000 square foot decision units. These were based on potential exposure areas, mainly just to give a good resolution for the property. You see one area here with it says DUs not shown. That was actually also subdivided up into exposure area decision units, about 10,000 square feet eventually, and tested. So you see here's the former Municipal Incinerator building here, source area DUs behind it, surrounded by perimeter DUs. We hope it come up clean. Let's go ahead and test the entire rest of the property, make sure we didn't miss anything. Turned out we would have missed a lot. The entire 10 acres was contaminated with lead above our action level of 200 milligrams per kilogram. So what it turned out to have happened is they were taking incinerator ash probably back in the 40s or 50s when the plant was operating initially, mixing it with fill material and redeveloping the rest of the property. So mixing the ash with fill material and filling in holes and such and leveling off the property. So the entire property was contaminated with lead. And needless to say, they're not going to use it as a soccer park now. It's being fenced off, and they're cleaning up the areas of the property that exceeded screening levels for commercial industrial use, and then they'll just continue using it for commercial industrial use in the future. But again, they went in and got out probably I think in 2 rounds of investigation at this site. They also did some investigations at depth. I won't go into that. Here's another property. This is the former power plant on the island of Molokai. The power plant has been out of business for 30 years. Proposed to be redeveloped as a community center. We knew in this area of the site, in this back corner here, we knew from historical data, interviewing people who used to work at the property and looking at aerial photos, this is where they used to take the transformers and out and dump the oil and replace it with fresh oil. So we had strong suspicion that this area could be contaminated with PCBs from just dumpage of waste oil in the past. Our office actually went out under a brownfields grant in early 2000s. Before we started doing multi-increment sampling, we collected 30 discrete soil samples across the site. It was 2 or 3 acres. So you can see here the results of the discrete soil samples. The areas in red are over 1.1 milligrams per kilogram. That's our residential screening level for PCBs in soil. And this is all surface soil data. So not a big surprise where we thought they were dumping the oil on the surface here is contaminated with PCBs well above 1.1 milligrams per kilogram. You see all these green dots around it. A little bit skimpy over here, but we were fairly confident we had isolated the main mass of contamination at the site. Keep in mind here, the samples when they're tested, we're putting 4 ounces of dirt in a jar, sending it to a laboratory. They're really taking out a random spoonful of soil, 10 to 20 to 30 grams, and testing that for PCBs. So all the lab data really represents is 1 spoonful of soil at each one of these green points, even though I have nice big green dots on the map. Well, once we start learning more about the unreliability of discrete soil sample data. Again, we'll look at that in the 3rd presentation. Under our 2nd brownfields grant, we went back to the site, divided into decision units for a DU MIS investigation. And again, where we thought the contamination would be located especially, we split these up into very small decision units, maximum about 3,000 square feet. Going down, I think we're potentially going down to 3 feet here or so. So we're looking at about 400 cubic yards of soil for each one of these DUs, characterized individually. And then in the outer areas, away from where we thought the contamination would be, we split those up into slightly larger decision units, up to the maximum decision unit based on exposure areas for commercial industrial size, a site of 10,000 square feet. So this large DU here, DU7, represented about 1,000 cubic yards of soil. And this may have been looking at the top 6 inches, I forget. So anyway, so we went back and actually collected samples at this site, and we'll show you what we found in the next presentation in part 3, looking at discrete sample data. And to give you a hint up front, we found a lot more contamination than we did with the discrete soil samples. And that's what we see pretty routinely, is that discrete soil samples tend to miss hot areas, hot spots, whereas you'll capture them with multi-increment samples. Here's another example. This is a former pesticide mixing area associated with a sugarcane mill. It's about 9 acres in size, right against the sea cliff oceans on the island of Hawaii, the Big Island. It's about proposed redevelopment for residential use. We're going to split the site up into 1 acre residential lots. So John and I actually went out to this site several years ago, and based on historical data, talking to people, here's an aerial photograph of the site. and looking at fire insurance maps in the late 1800s, early 1900s, we were fairly confident this area of the site, which turned out to be in here, was where they were mixing pesticides. We went out to the site initially and laid out a 5,000 square foot decision unit, which is our default for residential exposure. Tested it somewhere in this area here, and sure enough, it came up very high, hundreds of ppm arsenic. Now, the problem with this 9-acre site, it was going to take a long time. We were afraid to figure out the extent of arsenic contamination across the property. The consultant for the developer went out, actually got an XRF, and then collected 90 or so individual discrete samples across the site, represented by these blue dots. Each blue dot, he would collect a really good discrete sample from 3 or 4 or 5 or 6 or 9 points. So he'd collect several hundred grams of soil, put it in a plastic bag at each point, and then he shot each plastic bag or each discrete sample with his XRF. And then he very quickly, I think within a day, was able to map out where the main contamination was at the site. In the area, it was in the area where we expected, but covered a much larger part of the site than we would initially suspected. And one thing with this map, the boundary of the map you see is very squiggly and such. You really can't rely on this. We'll look at that again tomorrow due to small scale variability. Any one of these points, if you move over 6 inches, you could get an order of magnitude difference in the concentration of arsenic at the site. Also difficult to see on this, again we'll talk about tomorrow, you see these isolated hot spots of arsenic based on single samples or 1 or 2 samples. That's a key, a very strong flag that you may be dealing with small scale variability, and that this whole area right here below the main contaminated area could also be contaminated with arsenic above levels of concern. And if you move any of the sample points over a few inches, it may go from clean to heavily contaminated. So again, we'll talk about that more tomorrow, but discrete samples did a very good job identifying the main area of contamination. Next step was to divide the site into decision units, again for more detailed characterization. So the spill area, or now known heavily contaminated area, was divided up into fairly small decision units, I think a few hundred cubic yards, and that most of the contamination we already knew was within 6 inches to a foot. And this was used, the decision units were designated this size to assist in remedial options, or to set a resolution for remediation. So again, the next step then we'd go back in each one of these decision units, collect a single multi-increment sample, and then make a decision on whether or not to excavate and dispose of that soil. And we collect triplicate samples in 10% of the DUs within the spill area. Now the rest of the site we had reason to suspect was clean based on the discrete soil sample data. So in this case, the idea was to split the rest of the site up into hypothetical 1-acre residential lots, like we would anyway. And then we have a lot of discrete data within these lots, or hypothetical lots, but we want to go back to confirm that. We'll collect 1 multi-increment sample within each one of the DUs, and then a triplicate sample probably in one of the DUs, just to confirm these areas are clean. We'll look at tomorrow, or in the third presentation, on why just relying on discrete samples, even in areas you think are clean, may be a problem. We've had some sites we'll go back to the same area, collect another set of discrete samples, get a completely different mean concentration in UCL or contaminants within those areas. So here's another example. There's a lot of redevelopment in Hawaii starting in the early 2000s of the sugarcane fields. The sugarcane industry started to go out of business in the 1990s, and it opened up thousands of acres of ag land. And Honolulu's gradually been spreading out into some of these ag lands. So there was a need to test hundreds or even thousands of acres of former ag land for residual pesticides. So this is the approach we use for that. First, we have what we call a baseline investigation. This is what a developer would typically do, usually talking with our office kind of anonymously. They may not tell us where the site is, but before they the developer buys some large former ag land area, then they'll go out to the area, and then they split the area up into very large decision units, tens of acres or even hundreds of acres, based on the past crop history, pesticide use, soil type, topography, development plans, and such. There's really no set number. Typically a field they'll split up into 10 to 15 decision units. And then they'll collect a single multi-increment sample. You know, when they get this big, it may be 100 increments. We'll talk more about that again tomorrow and in the third and fourth presentations. But they'll have their consultant walk the entire property collecting soil samples from each one of the decision units. And the nice thing about this is that you'll find it allows you to check the entire property and be surprised what you find buried or dumps within the property you may not have known about before. They get a much better idea of the condition of the property. Then they get their data back. They can make a call on whether or not to proceed with potential redevelopment of the site based on large-scale pesticide residues in the soil. And then I can also use the data to select the primary contaminants of concern, which in Hawaii typically tend to be arsenic and DDT, organic chlorine pesticides, that were used as herbicides and mosquito control in the past. And they will collect triplicates in 10% of the decision units, typically one of them, just to check the field precision of their sampling method. Now, if they want a letter from our office, we require a smaller or a better resolution of the investigation to redevelop ag land into residential use. So we require them to test 59 random hypothetical 1 acre house lots scattered out throughout the targeted field. There's a statistical reason behind 59 house lots. If they all pass your screening level, then you can be 95% confident that 95% of the 1 acre lots you didn't test would also pass. So this is a typical approach for investigating very large areas, that very large ag land parcels that are being redeveloped for residential use. The nice thing with this approach is because the developer's typically first testing the entire property, and if a resident asks, did you test my yard, which is going to be economically impossible in most of these cases, just not feasible, they can say, we didn't test your yard, but we tested your neighborhood, these large DUs, and we tested a random number of lots. So this is a much better approach. In other states I've worked in the past, the recommendation for testing former agricultural land was to collect a single discrete sample every 4 acres. So imagine that. You go out to an area the size of 4 football or soccer fields, bend down and collect a random spoonful of soil and test it. There's not a lot of confidence that that random spoonful you test is going to be representative of that whole area. But this gives the developers a lot of legal protection in the future as part of just due diligence. So our guidance goes into more detail on these very large areas. For relatively small ag fields, less than 59 acres, because we're requiring testing 1 DU per acre, they're going to test the entire property because there'll be less than 59 1 acre DUs. And when you get to 59 to 118 acre size areas, then we still recommend testing 59 1 acre DUs randomly located within that area. And they'll be testing over 50% of the property. So our office will make a call on this if they skip the baseline investigation but just test 59 1 acre DUs. We're comfortable making a call on that field. As the field gets larger and larger, 118 to 590 acres, now just using the 59 1 acre DUs, it really isn't adequate. They're testing less than 50% of the property, so our office requires the person also to do a baseline investigation where they split the entire field up into very large DUs, sort of a neighborhood scale investigation. And once the field gets to be really large, say 590 acres, now these 59 1 acre DUs are covering less than 10% of the property. So we increase the number of a random hypothetical 1 acre DU residential lots for testing up to 90, and also again include a baseline investigation. There's some more details in our guidance. John's going to talk about this a little bit more in the 4th presentation on field implementation. So those are very large DUs. How about very small DUs? We also have a section in our guidance that discusses common problems and mistakes in site investigations using DU MIS methods. And one is, well, it's a small area. I'll just get a grab sample. I don't really need to do this MI stuff. Well, yeah, that's not actually true. The sampling theory still applies no matter how big your targeted area is. Under sampling theory, if you're looking at less than 2 millimeter fraction, you still need a minimum 1 to 2 kilograms of soil. This is based on the size of the particles, the shapes of the particles, density, and your target concentrations and such. So we'll talk a little bit more about that tomorrow in detail. But again, in this case, you would just spread your sample out across your targeted DU. Ideally, you're going to collect a single sample from at least 30 points within these small areas. So you can see here a leaking tank, an oil tank or something, obvious contamination there. Here's underneath that storm drain sediment. This is a site we're concerned about PCB contaminated soil and sediment running off the site. This is a storm drain, a sump, that then leads to a discharge pipe out into the woods. So in this case, we wanted to know if PCB contaminated sediment was getting off the site. So they pull the grate back. This vault is actually our decision unit. In this case, there's only 1 to 2 gallons of soil in the vault. So again, the thought might be, well, I'll just grab a discrete sample. It's a really small volume, but you still need 1 to 2 kilograms minimum. Or in this case, you just, because there's such a small volume of soil inside the vault, you collect the entire population, if you want to call it that, of soil. Put that in a bag. We typically use 1 to 2 gallon Ziploc bags, and you send the entire amount of sediment to a lab for testing. So you don't need to collect a sample because you collected the entire decision unit volume. Here's another example on the bottom right. We were talking to RCRA enforcement people at a conference once. A big problem they have, they're investigating illegal dumps, is they get the entry right to go into a property and collect a soil sample. They have to get in and get out really fast. As we were joking, as they were kind of semi-seriously joking before the owner sticks the dogs on them. So they go into a property. There's obvious potential problem in there. A lot of drums. The soil looks contaminated. Real quickly in the past, they would just throw some soil in a 4-ounce jar, a discrete soil sample, run and jump back over the fence before the dogs get them and have that tested. A big problem they have is the laboratory data come back and it's ND, and they know that soil is contaminated. They could tell in the field. The problem is, we're talking tomorrow, is that contamination soil can be really heterogeneous. Within even a small area, you might be able to find small pockets of clean soil within an area of much larger area of contaminated soil. So in this case, a much better way to do it is when you run into a site, very quickly designate your decision unit. It may only be the size of a barrel hoop or hula hoop or something, or 1 square meter. And then within this area here, again, collect a minimum 1 to 2 kilograms of soil. It's required under sampling theory for particles to get a representative sample. And then collect the sample from as many points within this area as you can before the dogs get you, ideally at least 30. Throw it in a bag, put it in your backpack, and get out. And then when the lab gets a sample, they don't just take the top of the jar off anymore. Now they've got a 1 or 2 kilograms of soil. They have to spread it out, sieve it, dry it, spread it out, and then subsample that and get a representative sample, subsample for testing. So then the sample data they get represents a sample they send in. Sample they send in represents this area. And not surprising, when you do this approach, you'll find a lot more contamination than you would with just single discrete samples. Those are very small DUs. There's more human health issues. Let's look at ecological decision units. This is another former skeet range on the island of Oahu. And here I had very good historical data. Even though it's completely overgrown now, it's been out of use for several decades. The consultant went out, looked at former maps of this area, aerial photos, talked to people who used to work there, and identified where the guns were actually being shot. And then there's a lot of information on how far lead shot goes and where skeet debris tends to fall. So the first thing they did was outline a really huge source area of where they thought the lead shot and the skeet were going to fall. You see here in red, they split that up into smaller DUs to get a better resolution of this area. Now, again, they're only looking in this case to begin with at the top 6 inches or so of soil. So this is what they used to investigate the source area. How about the surrounding areas? In this case, it's actually a wildlife refuge now. So they had their ecologists go out and look at the birds and such in this area, and they designated around 1 to 2 acre decision units based on mostly bird habitat around the skeet range. Just test those and confirm that these areas weren't contaminated with lead, or especially PAHs from the skeets. Then along the shoreline, a different type of ecological habitat here, wetland areas. So the same ecologist, risk assessor, designated smaller DUs along the shoreline based on depositional types, sediment type, the plants growing there, and the animals living in this area. So there's a third area of decision units, and then also wanted to test the sediment right below the low tide level here. Those are the blue decision units here. So a third type of depositional environment. So that's how they laid out the eco source area and eco-based decision units for this site. And again, they're going to go into each one of these DUs. They did, and they collected a single multi-increment sample from lots of points, probably 50 or 75, given we're dealing with lead shot and such. And so they get a single number for each decision unit, as if the decision unit itself could have been dug up, sent to lab as a single sample. And they found a lot of lead and a lot of PAHs at this site. Here's another sort of eco-based DU MIS investigation. This was an estuary on the Big Island in the town of Hilo. This freshwater springs discharged in the lower part of this estuary, which is DU2, and then it flows out into the Hilo Bay into the ocean. This is a very important mullet hatchery area. So John appeared in our office, oversaw this investigation. Along the edge of this pond, as they call it, the estuary, there was a former sugar mill, so right up front we're worried about arsenic contamination. Now they used arsenic in the 19-teens through 30s as a weed killer in the sugarcane fields. Anytime you're around a sugarcane mill, you have to especially be concerned about arsenic contamination. Also adjacent to this site was a former Canec plant. Well, the sugar mills generated a lot of waste sugarcane. It's called bagasse. In the 1920s and 30s, someone started getting the bagasse and making compressed boards out of it, and they would infuse the boards with arsenic to treat it with for a termite treatment. Now, if you don't treat your wood in Hawaii for termites, then your house will only last a few months, maybe a year. So it was a big boom, the Canec plant setting up here. But at this time, they were dumping the arsenic, wastewater from the process directly into the estuary, and later on they built a pipeline. It's the red line here, because they knew it was impacting the mullet here, and just started discharging the waste water further down into the estuary. So when John worked on this site, first he designated DUs based on suspect contaminated areas, especially around this Canec plant, and then also on the aquatic habitat areas, and you see in DU1 here, and then open areas within the estuary, DU3 and DU4, and then DU5 is where this wastewater pipe discharged. So that's how we designated DU decision units here. We also looked at sediment at different depths to see if there was some vertical limit to contamination. So here's an example at this site. Again, we did multi-increment sampling. We'll look at that more later. Each one of the DUs collected 30 cores. So John split the site up into targeted sediment DU layers. So we were looking at the top layer in each one of these DUs, 0 to 4 inches, and then 4 to 8 inches below that, and then 8 to 12 inches below that. So ideally, we were hoping we'd be able to isolate any arsenic contamination in one of these layers. Maybe the top layer was cleaner because the Canec plant had been out of business for decades, and new sediment had come in and capped the contamination. And then ideally, the deeper contamination, the deeper layers, we were hoping they would be clean also. So that was the idea, is to try to isolate the contamination within a specific layer within these DUs. But what happened this side is the entire estuary was contaminated with arsenic, and we're still working on that data. And in most cases, from the top to the bottom decision unit layer. Here's another sediment example. This is PCBs in front of an active power plant. We already had discrete sample data at this site, and the power plant is located right on the edge of Pearl Harbor. So there were some discrete soil sediment samples collected in front of the harbor and even up on the property. We knew there was PCB contamination in the sediment in the soil. So in this case, the consultant reviewed the existing discrete sample data, looked at suspect source areas, depositional environments, aquatic habitats, and designated, I think, 10 or 15 decision units based on these characteristics within the streams passing through the power plant and in the discharge areas and depositional areas. They split the sediment into 2 layers at each one of these DUs, 0 to 1 foot and 1 to 2 foot. Again, some of that was based on existing discrete sample data, and some of it was just based on site history and the desired resolution of the investigation. So you see here the gray boxes are the decision units, and then the colored boxes beside that just show what kind of contamination was found at it. So there's a misconception that these multi-increment samples will dilute out the concentration and you're going to hide contamination. It's the exact opposite when you do it in the field, because one sample is collected from so many points within a targeted area, you actually tend to catch the hot spots, and you'll find far more contamination typically than you would with discrete samples and at higher concentrations. So you see here they found PCBs in the sediment at several of the areas across the site. So that was some sediment and looking at eco-risk. The same approach applies to anywhere you're going to collect samples. In this case, this was an active industrial complex on the island of Oahu. There was some concern in the top right-hand corner here of industries, runoff from industries getting into some of the drainage canals that drain stormwater from this area into the ocean. So the drainage canals were split up into decision units for testing. Usually it's only a few inches of sediment in here. The DUs were typically 1 to 300 feet long, about 6 inches deep. So you're looking at only around 100 cubic yards of soil. Interesting thing with designating decision units, if you do field work, the neat thing is once you get out in the field, they're pretty obvious. It's pretty obvious how to designate decision units with just a little bit of practice. And again, we've been doing this for decades. But the idea of decision units, it forces you in the field to draw a line physically around your targeted area, and then you're going to collect a sample within that area. It helps you split up the site. So you see here in the top right hand corner is they're right at one of the industries. They're testing the sediment, soil running off, and rainwater from this industry. Along the middle of the canals here, some of them were ponded. So in this case, another decision, we're testing the fine grained sediment that's settling in the pond. You can see the guy here is in the pond, and he's walking down this tape, and he's collecting a multi-increment sample. So every few feet he's stopping and zigzagging back and forth across, collecting 30, 50 grams of sediment, putting it in a container, and then moving to the next spot. So that's how you collect a single sample across this one targeted area. And then another decision that we wanted to check to see what the sediment was like where it was discharging out of this industrial complex area. So right at the ocean outlet, we designated another decision unit there. Again, we're looking at the top 6 inches. In a lot of these areas, there actually wasn't much more sediment than 6 inches. And you can see outlined in red here, there's our ocean outlet decision unit. And again, we collect a single multi-increment sample in there. Now in the past, we may have done the same thing. We're always designating decision units even if we're drawing a line around it. Maybe we went into these DUs and collected 1 or 2 or 3 discrete samples. So it's something we seriously joke about. And most people know I used to be a consultant. How many discrete samples should you collect within one of these areas? Well, as a consultant, the answer was pretty simple because you often had the work plan handed to you after the fact. So you take the amount of money allocated for analysis of samples and you divide that by the analytical cost per sample, and that's how many samples you collect in the field. So very little science or thought giving to it. And that's what we get away from in these decision at multi-increment sample investigation approaches. It forces you to get everyone together up front, people collecting the samples, your risk assessors, your remediation experts, discuss how to designate DUs and how to collect samples within the decision unit. So you have the data you need when you get done. About excavation decision units, John mentioned this a little bit. So another big problem in the past we've had is you dig out with the contaminated soil, at least where you think it is, and you start collecting confirmation samples around the perimeter, and some of them fail and such. And you have to go back and do more excavation. There's really no clear endpoint at the site. The way you would do this under a DU MIS approach is that the floor and the sidewall of the excavations would typically be designated as individual DUs. They could be split up into smaller decision units. If you think most of the contamination, say originally before you excavated, was at a lower depth in the excavation, then you might split, say, DU2 into 2 different DU sidewall DUs. Same thing with DU3. Even maybe the floor of the excavation you may split up into smaller DUs if you want to get a better resolution to what's left in place. And I want to talk about this again in the third presentation. The nice thing with the DU MIS approach is for the excavation, you can go in and drill and collect your confirmation samples ahead of time. So you designate an area for excavation, that's your DU. You drill down through that to the bottom floor of where you intend to excavate, and you're anticipating the soil will be clean. So all these X's are increments where you collect a single sample across the floor of the excavation. At each one at these cores, you would collect 30 or 50 grams of soil, combine that into a single sample. So now you have a confirmation sample at your bottom of your excavation before you excavate. You can do the same thing on the sidewalls. You can designate your perimeter DUs around the edge of your excavation and then install borings within these DUs, collect increments from the borings, and there's a way you have to do this, make sure they're all evenly spaced between borings and between increments within a single boring. Again, you collect your confirmation samples up front. So then you excavate out your soil and you're done. You don't really need to collect additional confirmation samples, although in most times a consultant will do that anyway just as a second check. So you get in and get out. That's the biggest problem we've had in the last 30 years with doing environmental investigations, is getting no real clear endpoint in sight when you do these excavations or even investigation. because not enough thought was given into how you're collecting the samples and what they're supposed to represent. So now you've got a lot of soil from the excavation. Let's say also with stockpiles, you would still use the same approach, DU MIS, to investigate stockpiles. So in this case with stockpiles, for this particular stockpile, the developer wanted to use the soil in a residential development. There's really no reason to think the soil is contaminated, but in some cases they weren't really sure where it came from. They thought it was from a former agriculture field. So how do you test 1,000 cubic yards or several thousand cubic yards of soil for reuse in a, say, residential or even a commercial development? Well, you get back to risk assessment, or what's your question. And the idea is you're going to take some of this soil and spread it out across a residential lot, and you're concerned about the exposure of the residents to contaminants in the soil. So from a residential standpoint, our default is a 5,000 square foot lot. Let's assume a depth down to 6 inches. Well, that equates to about 100 cubic yards of soil. Maybe you're having larger lots, half acre, that's about 400 cubic yards of soil. So if you were going to reuse this stockpile for residential redevelopment, then you divide the stockpile up into 100 cubic yard DUs, or up to 400 cubic yards, depending on what you can use it for. Each one of the DUs, you're going to collect a single multi-increment sample. In 10% of the DUs, then you're going to collect triplicates. Again, the same as you would do in testing batches of samples at a laboratory. They don't run QC samples on every single sample they test. They do it for batches of similar samples. So in this case, 10% of the DUs, you're going to collect triplicate samples. And again, we'll discuss that again tomorrow. Then you compare the data for each sample and check the variability. If it's really close, you have a good sampling procedure and good precision on your data. If you're going to reuse stockpile for commercial use, typically you bump up the target DU volume to 400, 800 cubic yards. You're probably looking at half acre to even 1 acre exposure area sizes for reuse. So down to 6 inches, again 400, 800 cubic yards. Also, we do the same thing for dredge material, dredging in the harbors and canals in Hawaii. So for dredge material, in one case they were going to reuse the material for a beach replenishment. So we agreed on like 1 acre DU with 3 feet thick is what they're going to place this sand on the beach. So that worked out to be thousands of cubic yards per decision unit volume, and they would collect one sample for that. Again, once you start getting larger, more concerned about heterogeneity. So typically consultants will bump the number of increments up to 100 or so, and you can collect larger samples and have the lab test those. And we'll talk more about actually collecting samples like this in the next presentation. Let's look again more in detail in subsurface DUs. This is another pesticide mixing area. So one concern at this site was dumps that you couldn't see from the surface that had been just where people dug trenches or pits and buried debris. So they wanted to dig trenches across here and look at what was going on in the subsurface. We'd already tested the surface of this site for arsenic and dioxins in particular. So as they were opening up the trenches to look at the deeper soil, we had data for 0 to 6 inches. They simply split the soil up into decision unit layers at depth. So each decision unit would have several layers associated with it. Each layer would get its own multi-increment sample. In this case, all these bars represent where small bits of soil, 30, 50 grams or increments, were collected along the edge of the trench, combined into a single sample. So now we get really good data for that exposed edge of this DU layer tested for arsenic and dioxin. Same thing right below that. Ideally, this would help you isolate the depth of contamination at the site. You could also test the bottom of trenches for your targeted contaminants, just designated as a single decision unit. One problem is the floor tends to get littered with soil falling off the edges of the trench and such as they're digging. This is a great way to investigate a site. The backhoes are a lot cheaper than geoprobes or push rigs, and you can also see a lot more than you can by just putting in a few isolated borings or even lots of borings in here. This is actually the same site here. Here they do have a geoprobe out. Later on they went back and designated decision units at the site and then used a geoprobe to collect cores down through the targeted layers. So it's the same issue at this site. We want to get an idea of how deep the contamination went once we identified arsenic and dioxin contamination at the surface. So you split the site up into layers based on how deep you think the contamination might have gone, or from other sites, and based on remedial concerns. And then you're going to collect a single representative sample from each one of these layers in each decision unit at the site. Now, just because your targeted layer of soil, say down here from 2 to 3 meters, it's covered by 3 meters of soil doesn't mean that you go back to discrete soil sampling methods or whatever. You still need to collect a representative sample from at least 30 points within that targeted layer. So you simply drill down through the surface into that with your cores. You collect cores, and then each core interval that goes through your targeted layer is an increment. And we'll talk more about this, I think John will, in the fourth presentation on what you do then. So now you've got your 30 increments of soil from this DU layer, but the problem is your increments are really large. They may be, in this case, a meter long, and probably almost a kilogram more of soil. So you have to subsample your increments to prepare a sample. Just details in the field, though, on collecting samples, multi-increment samples. But again, from a decision unit standpoint, same thing. You split your decision unit up into targeted layers and then characterize the depth. Same as we would have in the past with discrete samples, but now there's more thought given to it. We're not just testing a pinch or spoonful of soil every 5 feet. Here's an example where that was done. This is actually our office we're about to move out of. It's being considered for commercial residential redevelopment. There was some concern in this area that there may have been lead contaminated ash mixed with fill material. And this whole area has been capped with 5 or 10 feet of fill material. So the new owner of the property wanted to confirm that the fill material under the site wasn't contaminated with lead. Didn't think there was, so they took a gamble. This is about 3-acre site. They split the site up into 2 large DUs in the parking lot area. Each DU they split up into 3 layers: 0 to 2 feet, 2 to 4 feet, 4 to 7 feet. So we're going to test. Think of it like a stack of books, stack of 3 books or a cake. You're going to test each layer for especially lead contamination. They installed 30 borings in each one of these DUs, collected core increments from each layer, and then subsampled those and prepared one single sample for each layer. So this site, 2 DUs, 3 layers per DU, we collected 6 samples. And they tested subsampling precision in some of those, which John again will talk about later. And one interesting thing with this, because they put in 60 borings in here, which would have been a lot less if we were just doing discrete samples, is one of the borings, sure enough, hit gasoline contamination over in the corner of the property. We have no idea why that's there, but we would have missed that if we had only done a few borings in a traditional discrete sample investigation. This would have caused a lot of headaches. If they started redeveloping the site, they had all their contracts and construction workers on site, and all of a sudden they dug in this area and hit gasoline, and that can shut down a project and cause huge headaches for the developer, as well as for the construction workers who suddenly can't work for a few days. Now, start getting more complicated sites. The more practice you get with this, and you can do really detailed investigations at a site. But again, you can get in and get out pretty quickly with just 1 or 2 rounds of investigation. This is a former sugar mill site on the island of Kauai, suspected to be contaminated with arsenic and dioxins. It shut down in the 1960s. So Laura Young in our office, her job is to actually go and look for these abandoned properties around the islands, and then we have our own internal field team. We'll go out and collect samples at these sites. We'll do a DU MIS investigation. That's really one reason I think, or it is the reason why Hawaii is so far ahead of the other states on this, because we have our own internal field team. So we go out and do this work ourselves, figure out what works, what doesn't, and then combine that with the experience of consultants. That's really what our TGM and guidance manual is based on. So here's an aerial photo from 1960 of the former sugar mill. There was sugar mill still then, general store, main mill, demolished in the 1980s, identified auto, truck body, truck building, maintenance areas. There's a stock building, a gym here, and this Laura was looking at the fire insurance map for the same mill and talking with people on what was this building, what was that building. And then right in here on the fire insurance map, 1960 Sanborn maps, it said, I think it said poison mixing or something like that. And that's the big red flag. That's where they were mixing arsenic-based pesticides or pentachlorophenol, which led to dioxin contamination. Big concern there. Laura actually found a picture from 1914. This guy he's on the poison crew. This tank, if you could read it, says poison. So this was arsenic. It was a water arsenic mixture. They would mix up inside of here, and then the workers would carry it out to the fields and spray it in the fields for weed control. So Laura looked at this picture here, and you see there's a wall behind it, and there's some trees and such. Actually, he was able to go back to the neighborhood and find out estimate exactly where that pesticide mixing was. Well, in the 1980s, they knocked the mill down and redeveloped the entire property for residences. So now there's single-family homes across the entire property. So we went out to the site. identified where we thought the former pesticide mixing area was, split up into really small DUs because it's going to be expensive to dig all this stuff out if we do find it. So from a remediation standpoint, in addition to risk assessment, so these are two house lots. We could have considered each house lot as one large exposure area DU, but we wanted some better resolution than that, so we split it up into 4 DUs. We'll look at those in a second, plus a drainage ditch beside of it. We're concerned about the houses around here, these open lots. Each one of these, less concerned about them being contaminated, so in that case we did consider the entire yard as a single exposure area decision unit. You can see these small green boxes here are just planter areas where there was some exposed soil, and then some drainage ditches along the side here. So we collected, again, one multi-increment sample in each one. We actually went down to 10 feet in some areas at this site with decision unit layers and tested mainly for arsenic and dioxins. Here's some pictures of the DUs. This is the house where we suspected where the former pesticide mixing area was. So again, instead of treating the entire yard as a single DU, we split it up into smaller areas. We had a DU for the front yard, a DU for the side yard, DU for the backyard. It's just two pictures of the same DUs. So we don't show all the DUs in here, I guess, but I think we did split it up into 4 decision units. Here's the drainage canal for storm drain right along the side of the house. These two houses here we suspected. So you can see here, here's the swale going through, so when it rains, all the rainwater goes through here. So we designated DUs within here just based on where we might have been getting deposition or runoff from the adjacent properties. I think we designated 2 or 3 DUs. We also tested the perimeter of that building where there was exposed soil as separate DUs. Again, like I said, we split, especially where we concern the pesticide mixing area actually was. We know from past experience that contamination can go down at least 10 feet. So we split the DUs around the house areas, former pesticide mixing areas, up into multiple layers to see if we get some idea of the depth of contamination and also get better resolution where the contamination was for future remediation. So typical DU layers for sites like this, the top 6 inches, 6 inches to a foot, and then 1 to 2 feet. Then maybe the other DU layers might be 1 foot or 2 or 3 foot thick depending on the site and the resolution you want. Here's what we found at this site to share a quick map. And this kind of gets back to the geology days, putting maps together. So you see right where we thought the pesticide mixing area was, sure enough there's extremely high levels of arsenic in the yard and moderate levels of dioxins. Main problem is arsenic. I don't think we show all the DUs here, but arsenic in some cases is up to 10,000 ppm. Luckily the soil here is very high in iron, so the arsenic was tightly bound to the soil. And it's still a problem, but it's only 10% bioavailable. So you can see the red, yellow areas where we found contamination above our residential action level, I guess yellow, and where it's in red it was above residential and commercial industrial. You see the surrounding lots here, either blue if for arsenic anyway, it was below our background level of arsenic in soil in Hawaii, which we use 24 ppm as typical background maximum. The green areas, there was a little bit of arsenic there above what we expect background, but it was still well below levels of concern for residential exposure. All these cross-hatched areas are areas where we weren't able to get samples because of buildings or paved or something, and we just extrapolated the data as a long-term management, just assuming the soil in these areas could be contaminated, and if they're ever exposed in the future, it has to be tested and managed properly. That was the map. Here's our cross-sectional view of contamination at the site. So here was the house, the main contamination here. The red here is where we did go down to 12-foot depth with multiple layers, and it was contaminated all the way down to the bottom. And we had surface samples here and a few other places where we went down fairly deep. But we used this to develop a cross-section. Again, we had an outer perimeter area here where the soil samples came up clean in the borings, and then the cross-hatched areas in between are just our estimates, or worst case of where the contaminated soil could be present that we weren't able to test, but has to be managed in the property. Again, doing this type of work, we found a debris pit on the other side of the house that we hadn't known about before. Grabbed some samples in the field with that, so I always reserve some money for additional samples for any surprises in the field, either within cores or setting up individual DUs. So this is the last big site, and we're getting more and more complicated here. This was a 4-acre site. A former asphalt plant was being shut down and potentially redeveloped for commercial use. In this case, the first step the consultant did, Again, initially think of the entire site as one DU, but then they looked at individual uses of the site, parking lot areas, maintenance, where the batch plant was, storage and dump areas. There's a wetland out here. They used this to split the site up initially. And then within each one of these areas, they went out to the field, talked to people, did inspections. They split these into smaller areas. They split these individual areas up into smaller DUs. They designate a total of 25 or so decision units at the site. So here's just an example of some of the DUs they designated. Areas where they didn't expect a lot of contamination, like DU2, 20,000 square feet. That's again about as large as we want to go for future commercial industrial exposure area. They were just storing gravel and stuff there, no obvious contamination. DU3 was another storage area where they had tanks and asphalt, cement, diesel fuel, discarded vehicles, scrap metal. They're a little bit more concerned about contamination here. They drew a line around that area, designated DU, about 7,000 square feet. That's pretty typical for an upper limit for a spill area, source area DU, where you really suspect contamination. Former UST pit, that was really small. They wanted to check for residual contamination at depth, only 240 square feet. But again, they used multiple layers to test the depth of contamination. Then another vehicle maintenance area, parts cleaning, lubricants and such, about 4,000 square foot area. Each area then designated as its own individual decision unit. Each one of the decision units has could have different targeted contaminants of concern depending on the use of the site. So this just shows some of the DUs, and then they're targeted COPCs, TPH, organics, and metals for each one of the DUs. At this site too is about 18 feet to groundwater, and they already knew they had some contamination, petroleum, and even PCBs in some areas. So I think in all the DUs, or at least most of the DUs, they installed 30 borings and split the site, the DUs up into layers 0 to 6 inches, 6 inches to 1.5 feet, 1.5 feet to 3 feet, 3 to 10 feet, then 10 feet to the capillated fringe, about 18 feet. So each of the DUs had 6 layers, and 1 layer including the capillated fringe. They designated the capillated fringe for groundwater as a separate DU because we were concerned about petroleum contamination on groundwater potentially migrating off-site. And we wanted to check for petroleum in the soil. And also install monitoring wells if we'd found any petroleum at the capillary fringe, which they didn't. So not all layers were tested for every DU, but you get an idea of that to a really detailed investigation. Here's what they found here. Also, you can see in the different DUs, they had metal contamination in some, heavy oil in some, PCBs and other. So really thorough investigation, no doubt. They had this site very well investigated, understood what kind of contamination was there. Now these are pretty complicated scenarios, the last 2 examples I showed. In some cases you're not going to install 30 borings at a site. It's just not going to happen. Say at a gas station or some active place where there's a building that's being used, you want to know what's under the building. So it's not going to happen. So we have a section in our guidance on single borehole DUs, which is something that field people have been using again for 20, 30 years. Say you're at a gas station site, you know your tank was leaking, you're trying to figure out what the lateral extent of contamination is. You do this based on single borings. So in the past we'd put in a single boring, say at a gas station site, and in every 5 feet or so of the core we just take one random discrete sample, which in the laboratory translates to a spoonful of dirt, and you'll miss contamination with this approach. Under a decision unit approach, each core, you would split the core up into targeted layers, as we're showing in this diagram. And that can be based on suspect, say, fill material at the top surface, or where you see petroleum contamination in the core. Let's say you wanted to know what the concentration of gasoline, or maybe it's a solvent within that section of the core. In this case, you would designate the entire section of core as a decision unit layer for characterization. Again, instead of collecting a random discrete sample out of each one of these targeted layers, then you would subsample that entire layer. Actually, if the core is small enough, you would just take that entire layer, put it in a Ziploc bag, and send it to the laboratory for testing. And they would dry it, sieve it, process it, and test it for non-volatiles. If it's volatile chemicals we're concerned about, John will talk more about that in the 4th presentation on field implementation. You would have a jar of methanol in the field with you, and you'd take plugs along that targeted layer, and you would put the plugs for each layer into its own jar of methanol, and that's what the lab would test for the targeted VOC contamination. So this is a good approach for identifying presence or absence of contamination. it's really hard to get an idea of concentrations. That's usually not a concern at this, say, petroleum site. You're just trying to map the extent of contamination. But in this case too, like we were discussing before, properties where you test the entire property. In this case, you're testing the entire core, sending that to the lab, splitting up the individual layers. So we've done studies in the field on subsampling the cores and testing them, and the more plugs you collect from a core and test within a targeted layer, the higher your concentration gets. So with discrete samples, you're really missing the hot spots in cores, even if you're trying to use a PID. There's more guidance on this in our technical guidance manual, more ideas. So that's single borehole DUs, making a single decision. Another place that consultants have been using this is looking at the depth of contaminated fill at a single point within an area. So you take a core, split it up into targeted layers, ideally at the bottom. Your last bottom layer is what you think will be clean, or the bottom two, and then you take that entire section of core as a single sample and have the lab process and test it. So it's a much better way to confirm, say, depth of contamination than discretes. This is I think my last slide here. So here's an example of one of these limited MIS and single borehole DUs investigations at this particular site. Again, they were concerned about lead contaminated fill under a building. I think it was a new buyer. Someone's going to buy the building. They're not going to put 30 borings through the floor of this active commercial building, but they did agree, or did decide to put in 3 single boreholes through the floor of the building. Again, they split the fill material under the building, or the soil under the building, up into targeted layers. In this case, they just sent that entire core section of the core for each layer to the laboratory for processing and testing. Now in the parking lot areas here, D1 and 2, again, for various reasons, they weren't able to put in 30 borings, like a minimum number of increments per sample. They could only put in 5. So they installed their 5 cores and targeted the same layers in these outside areas of the property. But they only had 5 increments per layer. And we know from experience that you'll miss a lot of contamination with that, probably underestimate concentrations of contamination. But they just wanted a big picture idea. Is this area under this building, does it have a lead contaminated fill or not? And even with just 5 increments, you may not get the concentration right, but you'll find out pretty quickly if you have lead contaminated fill under these buildings. Same thing in the single borehole DUs. I think at this building, when they installed their borings, did their cores, and they didn't find anything under there. So now the owner has pretty high confidence the fill under this building is not contaminated. So that was it. A quick review of example, maybe not too quick, example of decision unit designation. Again, it's critical at the front of the investigation through systematic planning to really understand your site and to put a lot of thought into designating decision units. So again, you want to designate decision units at the scale and at the resolution that you're willing to make a decision on afterwards. You don't want to do what we did in my past career as a consultant, go collect your samples and then get the data back and decide what to do. Decision units always have specific questions assigned to them. Does the concentration of lead in soil in this part of my backyard exceed a screening level or pose potential risk, yes or no? I collect my 1 sample MI with replicas to ensure precision, and then I make a decision based on that data. So you really want to avoid doing an investigation, making your decision units too large to make decisions on, and then finding out they're contaminated, and then trying to go back and re-subdivide the area into smaller decision units to try to get a better resolution on contamination. Sometimes that just happens. You think it's going to be clean, and again, with this type of investigation, the intensity of it, you find more contamination than you normally would. So you may have a very large DU that comes back contaminated when you thought it was going to be clean. So it might be in your cost benefit then to go back and split that area up into smaller decision units and re-investigate it. But at least there's still a more clear endpoint to the investigation than we've had in the past. So that's it for decision unit designation. The next webinar, I'll be back discussing sampling theory and then how to characterize these decision units in more detail. How do you collect samples? And we'll look at the reliability of discrete sample data that a lot of us have been using for the last 20 or 30 years, and we'll discuss multi-increment sampling methods in terms of sampling theory. So thanks for joining us, and we'll see you at the next webinar.